All right, so for this filters problem, example 1, if you look at what I was asking for, this is actually a woofer. If we go back to thinking about what I said earlier, that we're going to filter out the high frequencies. So what we need to do is design an RC low pass filter, parentheses, I'll put a woofer, at a cutoff of 250 hertz if we were given a resistor of 10 ohms. So if we know it's an RC, we already have the R. What we're going to design is we're going to design the C. So if we're going to solve this, I said every equation that you need is on the formula sheet. FC is equal to 1 over 2 pi RC. We know that is 250 hertz because that was the given, the FC right there, the cutoff, 250. 1 over 2 pi, 10 ohms, and we can solve for the capacitance. Capacitance, I'm just rearranging this equation, 2 pi 10, 250, and I get 63.66 microfarads. So if I needed to design it, I said every single low pass filter looks the same with a resistor that's in series and a capacitor in parallel across. So here is my output voltage. Here is my input voltage. And so we said we could have like a source here and a load here, but it's moving across. And here's the filter is what's inside of the box. So this right here is a 63.66 microfarad capacitor, and this is a 10 ohm resistor. Is it just me or is that really blurry?
That's like really blurry for me.
Yeah, it's really blurry for me too. It must be just the internet thing. Sorry about that. It is kind of clearing up, but yeah, that is blurry. You know what I'll do? I'll stop the video and I'll start it again and see if that helps. Still pretty blurry. Maybe it's a little bit better. All right, so part B, that was part A, right? We designed the filter. In part B, we need to calculate the gain factor at cutoff. Cutoff was 250 hertz. And that's a little bit clearer now. Well, maybe, right? And so at cutoff, we can calculate this. A shortcut, if you know it's at cutoff, if you just wanted to write 0.707 at the cutoff frequency, I would accept that as an answer. And that's because you're telling me I understand what the cutoff frequency is doing. I understand how this circuit's interacting. Maybe you did just memorize it, but this is a statement enough to say how filters work. But if you did want to solve it, right, and I wanted to say 1 over the square root R over XC squared plus 1, well, at FC, these cancel out. At FC, R equals XC. So that becomes 1, and that is 1 over the square root of 2, which is 0.707. The next one is the gain factor at 2 times FC, which would be 500 hertz. If I'm using this formula again, AV equals 1 over the square root of R over XC squared plus 1. What I need to calculate for is I need XC. So like Kevin said, we can just calculate for XC. XC, 1 over 2 pi. The F that we're using, right, this is when F equals 500 hertz. So now I can plug in 500, 63.66 microfarads, and XC is equal to 5 ohms. In here, I have 1 over the square root. Here's 10, here's 5, squared plus 1. What do we see happen there with that relationship? This is now 2 squared, plus 1. That's not a coincidence. This 2 at FC leads to the 2 of the ratio. Okay? Whenever I plug those in, I get a V 0.447. So my output voltage is less than even half of what the input voltage is. So it's filtering it out, which makes sense because we're greater than the cutoff, and this is going to let the low frequencies go through. So less than half of the voltage is what gets to come out. Let's do the gain factor at 0.5 FC, which would be 125 hertz. We need XC again when F equals 125. We can calculate XC, 1 over 2 pi FC, 1 over 2 pi 125, C 63.66 microfarads, and XC comes out to 20 ohms. AV 1 over square root of R over XC squared plus 1 over the square root. And I can just plug this in now. I don't even need to solve for it if I understand that. But if you need to solve for it, that's totally fine. This number right here is going to be 0.5, right? And the reason that is because that ratio of R over XC is 10 over 20, which equals 0.5, right? That is what this 0.5 is telling me. Ignore that, that's not a part of that. And then plus 1, that's still squared, and AV comes out to 0.894. So whenever my frequency is less than the cutoff frequency, most of the voltage is still there. That if my input voltage, if I had a voltage source that was 2 ohms, well, not 2 ohms, if my input voltage source was 2 volts, I could just multiply 2 times 0.894, and what gets out would be 1.788 volts. So most of the voltage still gets to go through, which makes sense because this one was less than the cutoff, and this is a low pass. So I got to pass through.